Can I start? Okay. Today I'd like to have some review on basic techniques on unification for propositional logic. Unification itself, the terminology of unification in computer science mainly comes from its applications in artificial intelligence, in other areas, in knowledge representation systems, and so. But after Silvio Ghilardi's works on unification for classical logic, for intuitionistic logic and classical modal logic, somehow it diverged from that line of applications in computer science, but other applications in admissible rules or some interesting questions arise before in the study of intuitionistic logic, classical modal logic have been found, and more or less the direction of research came into another road. So which we are going to talk about this road of unification. Just clarified at the beginning of the lecture that I'm talking about unification in propositional logic, which mainly has applications in the study of intuitionistic logic, classical modal logic, and the like. So let me first set the language which we are talking about. The language L0 is including the connectives together with a set var of variables which we indicate by a finite set at this moment, but it is not important. You can extend it to the infinite set of atomic variables. The language which we set is like this, and the question for unification in this language for the classical logic at first, we will always until my next announcement, we will talk about classical logic. The classical propositional language, we are having this language. The negation is a shorthand for a robot, and the unification problem for the classical logic states that given a formula in this language, how you can describe the set of all substitutions such that the result of the substitution will be a theorem, a valid theorem of classical logic. Exactly in apparatus to the question of solving a Diophantine equation in reals, exactly. So you are, for example, given with this formula, and you are seeking all substitutions, which means that by substitution in questions for reals, you expect that the substituted thing would be a real number. Here, you expect that the substituted thing should be a proposition in this language, in the same language of propositional language. So you expect that, for example, x1 would be replaced by some a, x2 with some b, and x3 with some c, and the result would be a theorem of classical logic. Of course, you can find some solution. That's not the point. The point is that finding the solution space, the set of all such substitutions which solves this question. For the classical logic, as we will see now, the answer is more or less elementary. You can use elementary tools such that describe the solution space for this question. But for intuitionistic, for the intuitionistic setting or modal language, it is somehow non-trivial, as we will see. Let me show for at the beginning for the classical case what's the situation. Uh, a substitution, let me set up the notion of substitution. A substitution is just a function that commutes with all connectives and only replaces atomic variables with some formula, as you expect. So a substitution theta unifies A in a logic, in a classical logic. So that's the definition. Theta unifies A if we have validity of theta of A in the classical logic. Then, given a formula, a proposition in this language A, the question is that given A in this language, find all theta such that unifies A. How we answer to this question? It depends. It depends on the situation about A. Either A is unifiable or not. It might be the case that A is not unifiable at all. Deciding this question is not difficult. It is just satisfiability question. You should first decide that is A satisfiable or not. The satisfiability coincides with the unifiability question here in the classical logic. Actually, if A is unifiable, of course it is satisfiable because just instantiate every variable in the substitution with some true false, your arbitrary true false value, and the result would be some satisfaction for that formula. And the inverse is even easier. If it is satisfiable, then the true false values is a substitution which unifies the formula as well. So unifiability is coincided with satisfiability here. If A is unifiable or satisfiable equivalently, which is decidable, of course, NP problem, but NP complete problem, but you can decide for sure. Then we'll go for finding the solution space for this question. Of course, we have when we find some satisfaction for this formula, we will have some solution for this question. But the main question is to find the solution space, the set of all substitutions which unifies that question. The interesting thing here is that this tool which we use for solving this question in general will be a basic elementary tool which we can iterate for other questions in other logics which are non-trivial actually. That's the main point that I started with classical logic. So basically we consider we start with some substitution tau, which tau is true false for any arbitrary unifier of A. Since A is assumed that, so let me first assume that A is unifiable. So F is unifiable, hence we may assume some tau such that tau of A is a theorem of classical logic. Then based on this tau, I will construct a most general unifier which describes the solution space for this question. I will describe theta of tau for variable x as follows. If A holds, then just take x. Otherwise, take tau of x. Essentially, this is telling that the idea is simple. The idea is simple. It says that you have two choices for defining the theta tau of x. It is either the x itself. Why we are taking x itself? Because A already holds. If A already holds, don't change it. Let it be as it is. But if A does not hold, then replace x with tau of x, which actually unifies A. We know that tau unifies A. The basic idea of many of currently published papers in this field of study is based on this trick. And then I can say that this theta tau actually unifies A, and more interestingly is that this is the best unifier, which means that all other unifiers are an specialization of this unifier. I will exactly define this notion. Let me first say why this is indeed a unifier of A. Assuming A in classical logic implies that theta tau of x is equivalent to x for every variable x, right? Because this will be eliminated and A will be eliminated, and the only thing will remain is x. So considering x implies this one, which implies that A implies by substitution lemma theta A is equivalent to A, which means that assuming A, the theta tau of A holds. Assuming not A also will implies that the theta tau of x is equivalent to this time tau of x. That's how it is defined. Then again, by substitution lemma, you can say that the theta tau of A is equivalent to tau of A. And since tau is a unifier of A, we can say that A implies theta, not A implies the theta tau of A. So we can conclude that A or not A implies that theta tau of A, which means that in classical logic, which this principle of excluded middle holds, we can say that the theta tau of A holds, which means that theta tau is indeed a unifier of A, which we expected. We defined it as we can see. But this is not the whole story. The interesting thing is this equation, which I would like to hold it out. It is telling that A implies x is equivalent to theta tau x. Such property for a substitution is called projectivity. This substitution is a projective substitution for A. Why the definition is it? The notion of projectivity comes from algebraic notion, which first used by and observed by Silvio Ghilardi in his paper, and used it by iteration. The interesting thing is this observation, which I currently want to say here, that if A implies this equality, then for arbitrary substitution lambda, which unifies A, we can apply lambda to both sides. Then lambda of A implies lambda of theta tau of x is equivalent to lambda of x. If we assume that lambda is a unifier of A, then we can conclude that lambda composition with theta tau is equivalent to lambda, which means that lambda is less general than theta, which means that theta tau is actually the most general unifier. It can generate all units. It is obvious that if you have a unifier, every specialization of that unifier will unify. That's the substitution theorem in classical logic. if something is a theorem, every substitution of that theorem is again a theorem. So one direction is trivial. If you can find one unifier, you can generate many unifiers. But the non-trivial part is that if a unifier is projective, then it is the most general unifier, in the sense that every other unifier is less general than that unifier. You can find something, the lambda is some specialization of the theta, which you already know that is a unifier. So the answer to this question for classical logic now is out. Given A, you can first decide that if A is satisfiable or not. If it is satisfiable, then find some satisfaction by some algorithm, NP algorithm that you have. Then let us call it tau. And then based on tau, define theta tau. And the theta tau is the most general unifier in the sense that every other unifier is a specialization of that theta. So more or less, you describe the solution space for this question, which we posed at the beginning. All other unifiers are instantiation of this introduced unifier. This phenomenon is called unitariness or projectivity of the unification type for the classical logic. So as a result, we can say that just a definition. Classical logic, the unification type for classical logic, unification type for classical logic is projective and hence unitary. Projective and hence unitary. The projectivity implies unitariness. It is general fact in every logic, even in intuitionistic logic. If something is projective, if some unifier is projective unifier, then based on that reasoning which I provided here, you can just use the substitution lemma and show that it is the most general unifier. So unitariness implied by projectivity, and it is global for every formula which is unifiable. You can find a projective unifier of that. Yes.
Maybe you could write down what is the definition because I might have to for now, but you probably said what they are, but it's the part before you.
Okay, I will. You want me to precisely define the notion? Okay. Okay, I was just wanted to skip this part, but if you think it is helpful, I will write the precise definition. We say that this is the definition. The definition for unitariness and projectivity and other notions will be provided here. We say that a logic, the unification type, the unification type for a logic L is projective if for every unifiable A, we have some projective unifier for A. What does it mean by projectivity? This means that there is some substitution theta which first theta of A is a theorem of L, and secondly, for every variable x, we have inside the logic L, A implies theta of x is equivalent to x. This is the notion of projectivity, which means that theta is a projective, and this is the unifierness. So we say that the unification type for a logic L is projective if for every unifiable proposition A, there is a projective unifier of that proposition. What does it mean by projective unifier? It means that there is a unifier of that proposition in the logic, which satisfies this equation for every variable x. Then we say that the unification type of the logic L is projective. So as a result, I can say that we can prove it easily now that if L is projective, then L is unitary. What does it mean by saying unitary? Let me first define the unitariness here and then prove this lemma. We say that this definition for unitariness of the unification type for logic, and then go for proving this lemma. As you expect, the unification type for a logic L is unitary if for a given proposition A in that logic, you can find a single unifier for that proposition, which is more general than every other unifier of that proposition. What does it mean by saying that more general? First, let me say, we say that theta is less general than gamma if and only if there exists some lambda such that lambda or gamma would be equivalent to theta in the logic. Actually, we set some logic in the background. All equalities are assumed as equivalency in some background logic. So within a logic L, we say that theta is less general than gamma if there exists some substitution lambda, which if you compose lambda with gamma, then the result would be theta within the logic L, which is given. So that's the notion of more general or less general. We say that gamma is more general than theta, or theta is less general than gamma. Okay. So, for example, if gamma is a unifier of A, then and theta is less general than gamma, then theta is also a unifier of A. So, as a trivial observation, we can say that if gamma unifies within a logic, I mean, is a unifies if gamma unifies A and theta is less general than gamma, then theta unifies A within a logic. That's because simply you are by this definition you are telling that theta is some composition of gamma, and by substitution lemma, if gamma unifies, if gamma is that only works for a logic which is closed under substitutions. So if gamma is a theorem, gamma of A is a theorem of a logic, then the lambda or gamma of that proposition is also a theorem of that logic. So this observation holds, and then we can define the unitariness. We say that the unification type of a logic L is unitary if every unifiable A for every unifiable A, there is a single unifier theta which is more general than every other unifiers of A, of course. So the unification type is unitary, is called unitary if every unifiable has a single most general unifier. So if by this lemma which I presented here, I would like to prove that if L is projective, then it is unitary. The proof is exactly as you can see here. If it is projective, then there is some projective unifier which satisfies this condition for A and the logic L, and then every other unifier of A by the substitution lemma for the logic is the composition of the same substitution with this projective unifier. That's it, and then the unitariness will be proved. So this lemma can be proved in the same way that we have seen for the classical logic. So with this example, one may have this idea that is the same beautiful manner holds, for example, for intuitionistic logic or classical modal logic or the like. The answer is no. For example, let me switch now for intuitionistic logic. In the intuitionistic logic, the situation is different. For example, consider this problematic example and simple example, X or not X. Of course, this formula in the intuitionistic language has two unifiers. You may replace X by top or bot. But a most general unifier cannot be found for this formula. Actually, it does not admit a single most general unifier. The reason is simple. Consider that A is a sigma. Let's sigma be a unifier of A. In, of course, all the rest until next announcement, I will talk about intuitionistic logic in the background. I will not keep saying that I'm talking about intuitionistic logic. So let sigma be a unifier of A, which means that in the intuitionistic logic, we have sigma X or not sigma X. Let's sigma X be some B or just write it as sigma X. Then by disjunction property in the intuitionistic logic, intuitionistic logic has some admissible rule called disjunction property, which essentially says that if in intuitionistic logic you can prove a disjunction, you are capable of proving either of the disjuncts. This property is missing in the classical logic. For example, the same X or not X, A or not A is provable in classical logic, but you cannot prove A at some places, and you may not be able to prove not A in classical logic. But in intuitionistic logic, it is not the case. Always when you can prove a disjunction, you can prove either of the disjuncts. And actually, you can. That's why you cannot prove A or not A. The principle of excluded middle PEM is missing in the intuitionistic logic, and that's why you have such a beautiful disjunction property for the derivatives. By the way, by disjunction property, if you can prove if sigma is a unifier of A, then you can prove this disjunction. And this means that either you can prove sigma of X, or you can prove not sigma of X. So this sigma has two choices by this conclusion. If a unifier of this formula A is considered, this unifier is either substituting the variable with truth or top, or it is replacing X with but and nothing else. So you only have two unifiers, and hence there is no most general unifier, because none of them is more general than the other. We can obviously and intuitively observe this, but proving this fact also is not difficult to show that these two unifiers which I mentioned is neither of them are more general than the others. So in the intuitionistic logic, the unification type for sure is not unitary, and for sure it is not projective, because if it was projective, then it would be unitary. The interesting and highly non-trivial fact about the unification type for intuitionistic logic is that it is finitary, which means that every unifiable formula can be the solution space for every unifiable formula can be calculated, computed, and it would be a finite set of most general unifiers, which means that every other unifier is less general than at least one of these finitely computed set of unifiers. I will go through through some basic steps and turning points in this proof. And then I guess this session I cannot go beyond the intuitionistic logic, the classical modal logic, but more or less the same story holds for the classical modal logic, which are transitive. There are some more details and some parts of technical lemmas, but more or less the same story holds, which means that the finitariness, the same proof actually, the same proof road actually holds for the classical logic. So the first step for the characterization of the unification type for intuitionistic logic is to characterize the set of projective propositions. Which propositions are projective in the intuitionistic logic? First, we characterize the projective propositions and then go for characterization of the unification type. Okay. We characterize the projectivity with Kripke semantics. Actually, this is all the results currently I am talking about is a result are published first in 1999 by Silvio Gulardi in a paper titled Unification in the Intuitionistic Logic. The reason that I started with this route of results is that at the end, I would like to give some generalization, which I made use of that generalization for the aim of the characterization of the probability logic of Heyting arithmetic. That's the basic actual fact that I used, and mainly the proof roads are similar to the proof roads for the paper published first by Silvio Gulardi. But the observation which I will give at the end of this talk would be nice. You will see. I hope you will consent with its niceness, but let me see. Okay. We know that intuitionistic logic is sound and complete for Kripke models. What is Kripke model? A Kripke model in classical logic, maybe you are not familiar, I will give some short description. In classical logic, you know that classical logic is sound and complete with respect to classical models. A classical model for the propositional language is just a true false value word in a word that every atomic variable is either true or false, and that's it. A formula is a theorem of classical logic if and only if it is valid in every word which is described by true false values. That's it. So this is the classical model. The intuitionistic model, a Kripke model for intuitionistic logic is a partially ordered set of these classical models. So you have a tree. We consider trees because trees are easier to treat. We have a tree of classical words such that if an atomic formula is valid at some node, then at every accessible node, this is the accessibility relation. We consider partially ordered such that there is no such return in these trees. So if atomic variable is an atomic variable x is valid at some node, then it should be valid at every accessible node. Validity could not be falsified at accessible nodes. And we know that conjunction, disjunction are interpreted as you interpret it in classical models, which means that a conjunction of two formula is valid at some node if both of conjuncts are valid. A disjunction also is valid if either of those disjuncts are valid. But the implication is some more or less interpreted differently, which means that at some Kripke model K and some word W, let us call this W, A arrow B is valid if for every accessible node U, for every U accessible from W, if K and U satisfies A, then K and U satisfies B. This is the definition for validity in implication, and that's it. We know that the intuitionistic logic, as I described as classical logic without principle of excluded middle, is sound and complete for these Kripke models. The point here is that you can describe the projectivity with Kripke models. There is a nice characterization, again due to Gilardi, that corresponds these two notions, Kripke semantics and projectivity, as I will state in this theorem. Theorem is that A is projective. By projectivity of A, I mean that there is some unifier, projective unifier of A. All I am talking about intuitionistic logic, so projectivity in intuitionistic logic. A is projective if and only if A has extension. The models, the Kripke models, the models of A are extendable. This theorem, one direction, let me first define what I mean by extendability. What is the extendability notion for the Kripke models? A class of Kripke models is extendable if, let me write it somehow an easier statement. If A is extendable, here I can define extendability easier. Before continuing with the proof line of this theorem, let me first define the extendability. We say that A is extendable if the idea is simple. Let me first describe the idea. The idea is that we say that A is extendable if there are finitely many Kripke models of A, then you can gather a new point beneath those nodes and define the valuation at this new node such that the newly constructed model is a model of A. So the idea is as I described, but the formal definition is as follows. We say that A is extendable for every Kripke model K such that K is weakly forcing A. We have some variants K prime of K such that K prime this time really forces A. There are two new notions in this definition. First, weakly forcing means that forcing A exceptly in all nodes other than the root. So you're separating the root and making exception about the root. A Kripke model is weakly forcing A if A is valid in all nodes except the root. So every Kripke model which is forcing A at every node except than the root, you can find some variant of that K. What does it mean by saying that a variant? A variant is a Kripke model with the same frame and the same valuation for every nodes other than the root. If you can change the valuation at the root, we say that the resulted model is a variant of the first model. So more or less, it is showing the same idea I described intuitively at the beginning of the definition, which essentially says that if you have a finitely many Kripke models of A, you can add some new node at the beneath of these finite nodes, and the resulted model would be a new Kripke model of A. You can choose evaluation. There is at least some valuation that makes the resulted model as a model of A. If A satisfies such condition, we say that A is satisfying extendability, or A is extendable. And the theorem is that projectivity is equivalent to extendability. One direction is easy. If A is projective, then for sure it is extendable. Let me describe why. Let A be projective. I will describe. I will prove that A has extension property or extendable. Let K be a Kripke model which weakly forces A, which means that a Kripke model that forces A at every node except then the root, maybe at the root it is not forcing. And we would like to show that there is some variant K prime of K which validates A not only at the non-root nodes, also at the root. Okay, the idea is that define K prime as follows. K prime is defined, we should use the projectivity of A. Since A is projective, so there is some sigma which is projective. Let sigma be the projective unifier of A. So we have a projective unifier of A called sigma, and then we define K prime and sigma of K. What is the sigma of K? Better to write it sigma star. Based on sigma, we can change the valuation at nodes based on sigma and result a new model, which is essentially defining the validity of an atomic variable as the validity of the sigma of that variable at the previous model. So the sigma of K is the new model, which its validity sigma of K at some node W, at some word W, is defined as follows, that that K and W would force the sigma of X. So sigma star of a Kripke model is just defined based on sigma, the substitution sigma. And you can prove that if sigma star of K defined in this way, you can prove that the same holds for not only variables, for every formula, the same holds. By induction on the complexity of formula, you can prove easily that also for every B, formula B, the sigma star K of K and W forces B if and only if K and W forces the sigma of B. This would be a simple observation. So let us go back to the proof line of this equivalency of projectivity and extendability. Then you can prove that, okay, consider K prime as sigma star of K, then you can prove that this K prime is a variant of K, indeed. The reason that K prime is a variant of K is that sigma was a projective, and every node other than root A so is whole at the Kripke model. So the sigma star of K at the above nodes, the nodes above the root, is equality, because sigma of X is equivalent to X at the nodes which are above the root. So indeed, sigma star of K is a variant of K. And why it is a model of A? The reason is that the sigma star K is a model of A because K is a model of sigma A, because sigma A is a theorem of intuitionistic logic, and intuitionistic logic is sound for Kripke models. So sigma A is valid at K, and hence sigma star K at every node validates A as well as the root. So this direction is easy, but the other direction is not easy. The interesting fact about the other direction is that you should construct a projective unifier. If given this fact that A is extendable, you should provide some projective unifier for A. And the method for providing such projective unifier is by combination of, by iteration of the previously defined projective unifiers for the classical logic. Actually, you should iterate it at many times, and the result would be the construct. I wouldn't go to the details of this proof, but just sketching the idea. Okay. Then, based on this characterization of unification, this characterization of projectivity, you can prove that. Again, I will provide a proof idea. we can prove that given A then a unifiable A. So we assume that A is unifiable. Again, in the intuitionistic logic, a formula is unifiable if and only if it is satisfiable. Again, satisfiability and unifiability coincides in the intuitionistic logic algorithm. A unifiability problem is not non-trivial again, but is equivalent to the satisfiability problem. Given a unifiable A, there is a finite set of unifiers that are more general than every other unifiers. What does it mean by more general than every other unifiers? I mean that every other unifier of A is less general than at least one of the members of this introduced set of a finite set of unifiers. The proof idea is as follows. I wouldn't go through the details, just would like to have a flavor of the proof. How does it prove?
When you say that the are more general, you mean for every other unifier, one of them is more general, or all of them are more general?
At least one of them.
Okay.
Let me the idea is as follows, that given A, this A has the nested implication complexity, some fixed nested implication complexity like N, let us call N. N is the maximum number of nested implications inside A. And then for every unifier sigma of A, let sigma be an arbitrary unifier of A in the intuitionistic logic, we will find some B. We will find some B which has less complexity than N. Its complexity of B is less than N. What is the C of B? The complexity of B means that's the number of nested implications inside B. We will find some B which has less complexity than N. There are finitely many such formulas. It is, although in classical logic, we know that by finitely many variables, you only can provide finitely many unequivalent formulas. In intuitionistic logic, such a formula, even for a single variable, does not hold. Even for a single variable, you can find infinitely many inequivalent formulas. But if you restrict the number of nested implications, there would be a finitely many such formulas. By the way, given a sigma unifier of A, we will find some B which has a complexity less than N, which means that essentially there are finitely many such Bs, such that first of all, B implies A, and secondly, B is projective. The idea is that even so if you want to find a finite set of a complete finite set of unifiers for A. Just consider all projective formulas which are implying A and have less complexity than N. And the projective unifiers for those formulas would be a complete set of unifiers for A. That's the idea. And how is it found? Now I will describe how you can find such as the final step. I will leave the routine check for this fact that I mentioned here, that if you can find such B, the proof of the finitariness would be finished. But let me show how to find such B. The idea is that you will consider a class F of Kripke models, which includes the sigma star of every Kripke model K, such that K is a model of A. So you will consider the sigma star of every model of A. This is a class of Kripke models. Then by some techniques, you will saturate this class of Kripke models. Let us not go through those saturation, because that saturation is a technical and not a big deal with this saturation process. So I don't go through this saturation. Just assume, consider this class of Kripke models. Then basically you will show that F is the class of Kripke models which are mod of some B. So basically this is not exactly the same. You should complete this class, saturate this class by some extra Kripke models, but more or less it is the same, not a big deal with this saturation process. So for a moment, for the simplicity and observing the main road in the proof, F is considered, is shown to be a model of some proposition B, and this B should be projective. Why? Because this class of Kripke models has extension property. By extendability of this class of Kripke model, you can say that B is projective. Why? Because we already characterized projective formulas as exactly the class of propositions which its class of Kripke models are extendable from below, and this class of Kripke model is extendable, and it can be shown that it is a model of some B. And the only thing which I didn't explain in detail is that why such B has less complexity than A. That's why you should saturate this class of Kripke model. Actually, the reason that you should go through some details, technical details that I told you, is that somehow enrich this class of Kripke models such that the resulted class would be a model of some proposition with less complexity than an arbitrary formula. That's the only fact which you should take care of, which I don't go through the details. That's it. So you can prove the finitariness of this logic. Now, just not to making you bored, at the end I will sketch what is the generalization I considered over these constraints. In going back to the first question in the Diophantine equation, in a Diophantine equation or an equation in real numbers, you always consider some parameters. It is not the case that always all the things are variable. Then the equation would be somehow trivial if you only consider an equation with variables. You always have some parameters. For example, an equation there includes 3 parameters and 2 variables, and you seek for all substitutions such that the equation would be solved. The same in the logic also would be appreciated if you would permit some parameters which you don't like to be substituted, and considering some parametric version of this unification problem. So the parametric unification problem goes for an extended language. Let us call it L0 par, which is just L0 plus a set of parameters indicated by some set of parameters. You can consider it infinite or finitely many of them. That's not a big deal. And then consider the same question of the solution of the unification problem for the parametric version. This parametric language is considered by in the admissibility field of study by Rybakov and others. For example, admissibility for this parametric version has been resolved, the decidability of it. But the unification and projectivity for this parametric version has not yet been settled down. Actually, that's what I considered and observed, that, for example, in parameter-free language, the situation was simple in the classical logic. Every formula was either anti-theorem, which means that it is false always, or it is unifiable and projective. That's the result for classical logic I started with. Here in the parametric language, we should restrict the substitutions which does not replace parameters, of course, as you expect. So the unification problem would be this, that given A in the language of, in the parametric language, describe all theta such that theta of A is a theorem of classical logic. But theta has some implicit requirement. This requirement is that theta can only replace atomic variables and is not allowed to replace parameters. Parameters should be untouched. Okay, so the question is the same. And one way to think about this question is that just consider this question as before, and then you will have the usual notion of projectivity and unitariness and the like. But it is not in my opinion, it is not the right viewpoint for considering projectivity. Actually, the right thing to do here is to, because you will lose many meaningful information. For example, P1 arrow P2 is some formula, some meaningful formula, which is not projective in this regard. You cannot unify this formula because you cannot replace, even this simple formula is not unifiable. And it is not anti-theorem at the same time. In non-parametric version, every formula was either unifiable or anti-theorem. So the situation was simple. But here you will lose many of these intermediate formulas and even more. For example, you can have a parameter conjuncted with an arbitrary formula. And again, this formula is not unifiable with the same reason. So many of the meaningful formulas which you expect to be in contact with the notion of projectivity will be lost here. The idea is that instead of searching for all unifiers, search for all parametrifiers. I mean by parametrifying that search for all substitutions theta such that the theta of A would be in the Boolean combination of parameters. This would be some generalization of the notion. This way, you will have, for example, that this formula can be instead of unified can be parametrified, and also this one and many other formulas. And interestingly, if you restrict the language for the empty set of parameters, the question would be the same as the usual unification in the classical logic, except for that extension that you will add what and top. Instead of unification, you will be interested in unifying or anti-theoremizing, which means that you will be interested in all substitutions that unifies it or make the negation of its unified this extension. By the way, the idea is that we consider this question in the classical logic, and with this extension you will again have some beautiful characterization of all this relative unification question. The question which I considered was not for the classical logic, because I was not at that moment interested in the classical logic, and more or less it is trivial. You can go for it yourself with this definition I explained. The question for the intuitionistic logic, for parametric unification for the intuitionistic logic, was the thing which I was interested, based on some idea that I was thinking at that moment that it would be applicable in some long-standing open question of probability logic of Python arithmetic. And finally, I made it actually based on a characterization of relative unification for the intuitionistic logic, which essentially was the intuitionistic version of this notion for classical logic. It requires some more concepts like nil propositions, the class of non-nested implications in the left, which at this session I cannot embed it. Maybe at some other session I can explain, or if you are interested, I can address it how, or I can discuss in one-to-one discussions. By the way, I would like to grab your attention that this relativization of the unification had at least one application for me, that I could use this for the characterization of the long-stand open question of the probability logic of Heyting arithmetic, and also the outcome characterization for parametric unification type would be nicer than just considering the usual unification in the parametric language, because this way you wouldn't lose treatment of such examples I explained here. I tried to convince you that why one should consider a relativized version of unification instead of the simple unification for this parametric language. All right, I guess that's it. If there is any question, I will be here.
All right. So I guess I don't know. Correct, but okay, when I was thinking about the communication, what comes to mind is that after the connection with well, quite all this, maybe I have the following in mind. So, one kind of way, or one be able to say that you got some logic to find unification type would be something like. So basically, if you consider, say, the set of formulas ordered by this generalization order, right? So when you introduce one formula from other by some kind of substitution, so let's say that if say the formula that is produced is smaller than the formula from which it was produced. So then I think basically if the substitution is a generalization order would be well by the order, then it would imply that the corresponding logic has fine unification type, simply because when you have some formula, right, so then you could consider the set of all so the set of all its unifiers, right, and then it will be of course downward set in the generalization order, and hence if the order would have been well by the order, then automatically the set of your set of more general unifiers will be the set of maximal elements in the downward close set. And like this is basically definition, one of the possible definitions of quality orders is that order says that for in any downward flow set, the set of the set of maximum elements is finite.
Well, not really. Yeah, you also need to be well founded. But otherwise, like,
yeah.
you get that. But yeah, that's what was missing on it. But it's missing.
Yeah, yeah. So, yeah, I was thinking basically, do you also get well quality orders of this generalization order here, or
That's interesting. That you observed that. At this moment, I'm not sure if it is easier to consider this to prove this property for more general.
No, I mean, of course, this seems to be more general property, right? So because I mean, I don't want to actually it's true, but like
So
what's and what I'm saying is
so I couldn't get what's your point. So
No,
this generalization is somehow implies the notion of
right. I mean, okay, basically this generalization order would be well like the order then like this finite the implication to the kind of implication type of finite is trivial. Oh yeah, yeah. Basically, my question was whether it's actually true that this order is developed by the order, because this I don't know.
I see.
Yeah, it was kind of.
I haven't looked this way. I should think more. At this moment, I don't have any idea, but it makes sense to be. Everything that at this moment comes in my mind is compatible with being well quasi ordered. But maybe I should think more.
Okay. No, of course, just say, essentially, of course, like it's again about like the fact that like the math for it's sort of kind of downward flow therapy. The set of maximum elements will be finite, yeah, and this is kind of in some sense effectively designed, but required for all exactly. This is just very much like okay.
Thank you. Actually, one comment. No one has questions, so I will add this comment that the idea for considering this relativized version for the classical logic came into my mind yesterday, and I didn't consider it. I don't know why I directly went. The reason was easy, but maybe it is interesting to consider this relativized version for the classical logic at first. It is something like some exercise, not something for publication, but it made me to be excited because somehow you can establish the extra value for considering such relativized version. That's the final comment for this generalization. Okay, thank you again.
I guess. So who's speaking next week? I guess, but I guess I think we write about this. So we have two speakers. But I said we will be reading that first.